Welcome to day 34. So picture this. You've spent weeks, maybe even months building a machine learning model. You've finally hit a great accuracy score, but then someone asks you a simple question. So how does it actually work? And suddenly, you're just staring at a black box.
Let's tackle that question head on. Let's say your model has 90% accuracy. That's great, but can you actually explain why it's making the predictions it's making? Because a lot of the time, the why is just as important as the what.
And this, right here, is the classic black box problem. We see the inputs going in. We see the outputs coming out. But what happens in the middle is a complete mystery. By the end of this, you'll have the tools to actually peer inside that box and see what's driving the decisions.
Okay, let's dive in. The key to unlocking this whole black box thing really comes down to a pretty simple but powerful idea: figuring out which of our inputs are actually pulling the strings.
And there's a formal name for this: feature importance. At its core, it's just a set of techniques that assign a score to every single input feature. That score tells you how much it contributes to the model's predictions. Simple, right? A higher score just means it has more influence.
You know, a great way to think about it is like you're baking a cake. You've got all your ingredients: flour, sugar, eggs, butter. Feature importance is kind of like the recipe telling you that the sugar and flour are absolutely essential, but that tiny pinch of salt, maybe not as critical. Without that guide, you're really just guessing.
So why does all this matter so much? Well, for one, it lets us understand and actually trust our models, which is a huge deal in fields like finance or medicine. It also helps us improve our models by getting rid of noisy, useless features. We can use it for debugging too, to find out why a model is making weird predictions. And maybe most importantly, it helps us explain the model's logic to other people. Now, there are a bunch of different ways to calculate these scores. To make sense of them all, it helps to think of them as falling into two main camps, or two different philosophies for how to investigate a model.
On one side, you've got model-dependent methods. These literally look inside the model's internal wiring, kind of like an engineer reading the blueprints. On the other side are model-agnostic methods. These don't care what's inside. They treat the model as a black box and just poke at it from the outside to see what happens, like kicking the tires on a car. The trade-off is pretty clear. Dependent methods are fast and specific, but they only work for certain models. Agnostic methods are super flexible, but their insights are based on behavior, not the internal mechanic.
Okay, enough theory. Let's make this way more concrete by looking at one core technique from each of these philosophies.
First up, we've got a model-dependent example that's perfect for models like random forests. With these, we can look right under the hood to figure out what's important.
So here's how it works. In a decision tree, every split is basically a question about a feature that's trying to separate the data. The model then measures how good that split was by calculating something called reduction in impurity. Just think of impurity as chaos, right? How mixed up your data is. A really good split creates two groups that are way purer or more organized than the original group. So the features that consistently make these powerful, chaos-reducing splits get ranked as the most important.
Next, let's check out a model-agnostic example: permutation importance. This is a really clever and intuitive technique that you can use on literally any trained model without knowing anything about how it works inside.
The logic here is just really elegant. First, you get your baseline score. You just measure your model's prediction error. Then you pick one feature, and you break it. You just randomly shuffle all the values in that column, which totally destroys any relationship it had with the outcome. Then you run the data through the model again. What happens to the error? Does it skyrocket? Well, if it does, you just broke something really important. And that increase in error, that's the feature's importance score.
Okay, so we get the theory, but how do we actually use this stuff day to day? When do you pull these techniques out of your toolkit?
Well, first up, feature selection. If you've got hundreds of features, you can use this to find the vital few and build a simpler, faster, and often better model. Second, it's great for debugging. If your model is giving you strange results, feature importance might show you it's relying on some weird feature you didn't expect. It's a fantastic sanity check. And finally, for communication. It's one thing to tell a stakeholder your churn model works. It's way more powerful to say it works because it learned that the number of customer service interactions is the single biggest predictor of a customer leaving.
So, to wrap it all up in one sentence, feature importance gives us a toolkit to quantify how much each input drives a model's output, making these opaque systems a lot more transparent.
So here's the key takeaway I want you to remember. When you need to understand your model, you have a choice to make. Is it better to look at it from the inside out or from the outside in? You now have a framework to go and find out which features are truly driving your model.